Okay, so the title of today's webinar is, as you can see, Europa Clipper and Ocean Distribution in the Solar System. Firstly, I would like to show you what you can expect from this webinar. So I will show the contents. First, we'll be discussing Europa Clipper spacecraft as well as the mission. I will be telling you about the general info. We'll be focusing specifically about the instruments. So the not engines, solar arrays, and coating won't be discussed that deeply. It will be very brief. Next, I would tell you something about moons that we suspect that have subsurface oceans, especially 6 of them, and what's interesting about them, what differs, why they are different from the others. The third part would be, I titled it Europa Case Study, because I won't only be telling you about the features of Europa, but also how we know it that those features are like this, what measurements we made and expecting to make with Europa Clipper mission. The second to last point will be a comparison with Earth's timeline. So I will be discussing what we expect in terms of like organic life compounds on subsurface oceans of the moons. And at the end, I will be discussing references. There will be some time for questions, and also I will be recommending other sources, because here, as you can see, it's a like wide range of topics, so I won't be able to discuss them very deeply. So if somebody will be more interested in specific topic, I hope I will be able to give them a relevant source. So beginning, I would like to present to you some general info about Europa Clipper. So it was planned to launch on 10th of October 2025. However, due to harsh weather conditions, it was postponed to 14th of October. Europa Clipper spacecraft spans with its solar array wings 30 meters. At launch, the spacecraft weight was 6,000 kilograms. Its dry mass was 3,250 kilograms. So dry mass is the mass of the spacecraft without the propellant, so without the fuel. The fuel of Europa spacecraft at the launch was almost half of the total weight. Europa spacecraft has 9 science instruments and 10 science investigations. One investigation's gravity and radio science does not require any additional hardware, so there's no additional instrument, but it's using just the antenna that already is on Europa Clipper. Europa Clipper has 24 engines. It will complete nearly 45 to 50 flybys by Europa. Yes, those will be flybys, not like it won't be orbiting Europa, because Europa is very close to Jupiter, and Jupiter has a very strong magnetic field, which would just fry the electronic inside the spacecraft. The closest distance to the Europa's surface is expected to be around 25 kilometers. Europa Clipper already used one gravity assist from Mars on 1st of March 2025, so not so long ago, and it's expected to use another gravity assist from Earth on 3rd of December 2026. It is expected to arrive at Jupiter's orbit on April 2030. and it will spend around like a year on this orbit to alter the trajectory of the spacecraft to prepare for the first Europa flyby. So now I would like to move to the instruments. They are categorized into 5 categories. Each category has 2 instruments only, or more precisely, 2 science investigations, and I will try to distinguish those instruments from each other, what they are responsible for and what they will do when they will be at Europa's flybys. So the first category are the cameras, and we have EIS and EFEMIS. You can see here on the presentation, those are the 3D computer models from Jet Propulsion Laboratory. And what's the difference between those 2 cameras? It's quite simple, because EIS is responsible for the visible light spectrum, and EFEMIS is responsible for the infrared light. In depth, you can see also here on left, the model on the right, the red is the location of the device on the spacecraft, and EIS consists of 2 cameras, WAC wide angle camera and NAC narrow angle camera. Both of them have 8 megapixel sensors, and in total, after all the flybys, we are expecting to map 90% of Europa's surface. So we'll be looking at the specific surface features like elevations, plumes, so the water geysers, and maybe surface composition. EFEMIS is responsible, as I said before, for mapping Europa's surface in infrared light. More accurately, it's responsible for mapping the surface temperatures. Those temperatures will show us where the thickness of the ice on the Europa is smaller, where it's thicker. Also, with that, we'll be able to detect plumes or near surface liquid water. Next instruments are responsible for spectrometry. We have Europa UVS and MISE. The difference between them is that UVS is responsible for ultraviolet light. MISE is responsible for infrared light. Those are both spectrograph and spectrometer respectively, and Europa UVS will be collecting ultraviolet light from the structure of Europa's surface and atmosphere. It's, I think, important to say that ultraviolet light has very small wavelength and high energy. Because of the small wavelength, it won't be able to pierce through the surface. It can very easily be stopped. So mostly with Europa UVS, we'll be mapping will be collecting and gathering data about the atmosphere and the surface. We'll be looking at the spectral decomposition, so the elements and chemical compounds that the atmosphere and surface consists of. Next is MISE. So it will be it's a spectrometer that's more responsible for the infrared light. So it will be trying to map the distribution of ices, so the different kinds of ice, because in space, ice, because of the specific conditions, may have different lattice structures of salts, organics, hotspots. Because of being infrared, it will be able to pierce the surface of Europa and show us the subsurface specifics of the subsurface. Next category of instruments are plasma and magnetic field. it's quite easy to tell the difference between them, because ECM is responsible for the total magnetic field, and PIMS is responsible for magnetic fields connected with gathered plasma around the exosphere of Jupiter. And more precisely, ECM will be continuously measuring with its sensors orientation and strength of the magnetic field. Jupiter has a very strong magnetic field, and also from Europa, we believe that from the subsurface ocean, there's the salty ocean will be helping to induce the magnetic field back. So we also will be measuring this. However, the problem with that thing is that around the exosphere of Jupiter, there will be a lot of plasma. It's because of the Io, another Jupiter's moon, which is very volcanically active. It's, I think, the most volcanically active place on our solar system. And it will be ejecting many particles that will be charged. And because of this charge, they will be interfering with the magnetic field. So ECM and PIMS will be collaborating with each other, and the contribution to the magnetic field calculated from PIMS will be subtracted from the readings of ECM. So yeah. Next, we have radar and gravity. Gravity radio science, as I said before, it's not an instrument itself. It's the antenna and other hardware on Europa Clipper. And we have reason. The difference between those two is that GRS is responsible for capturing and sending back radio waves between Earth and Europa Clipper. And Reason is responsible for sending radio waves directly into Europa's surface. Those radio waves will be reflected back and will be measuring the differences. I will more deeply discuss GRS later, because it's closely connected with one specification of Europa and Jupiter. But yeah, it will help us map the exact location of the Europa Clipper and how the distribution of mass on Europa is affecting, so accelerating or decelerating the spacecraft. From this decelerations will be able to map the mass distribution on Europa. Reason, which will be sending radio waves. Radio waves have even greater wavelength than infrared light, so we'll be able to pierce into the subsurface ocean with those waves. They will be reflected back, and we'll be able to study the surface composition, roughness, plume activity. We will be able to confirm that the ocean exists, and we'll be examining the shell's internal structure. The next pair of instruments are for the chemical analysis. Both of them are very similar because I will discuss shortly what they do. However, the difference between them is that mass specs is concerned with the gases, and SUDA is responsible for the meteorites. It works like that. The mass specs will be collecting gas from the atmosphere or from the plumes. I will be discussing also later the plumes, so the water geysers, and it's ionizing the particles, so giving them a charge and moving back and forth through the spectrometer. And with that, we'll have spectral decomposition. We will know what the atmosphere and plumes are made of, what elements, chemical compounds. SUDA will work very similarly, because there are a lot of meteorites, small meteorites that are on the surface of Europa, and they are ejecting rocks from Europa to its orbit, and SUDA will be gathering these rocks, dust. It will be also ionizing it, moving back and forth through the spectrometer, and we'll have spectral decomposition of the surface of these rocks that are ejected into the atmosphere of the Europa. Next is I would like to discuss moons in the solar system that we suspect that have oceans. I have chosen 6 of them. Maybe not I, because you can see here on a picture there are 6 moons compared to Earth. They are to scale, and it's by Kevin Peter Hunt, and his book is what inspired this webinar. It's, I think, in English, Alien Oceans. Yes, so now I would like to give you some general info about these moons. So 3 of them are Callisto, Ganymede, Europa, are the moons of Jupiter. There are 3 from 4 Galilean moons, so discovered by Galileo. And the other one, the 4th one is Io, so the one that was responsible for the plasma readings. We have also 2 moons from Saturn, Titan and Enceladus, and we have 1 moon from Triton, Neptune. Why I'm concerned so about the moons and not, for example, about the Uranus, Neptune? We know that Uranus and Neptune do have oceans. However, the conditions are very harsh, and we don't think that there are habitable zones on them. You can see also that the sizes of those moons are pretty significant, are between like 1,300 kilometers and 2,600 kilometers. The only one standing out is Enceladus, which is like order of magnitude smaller, with radius 250 kilometers. They have similar orbital periods. Also, Enceladus is, I think, the most standing out one. And I also have shown the distance between the object they are orbiting. Some of you may ask why moons? Aren't moons like very small compared to like planets, insignificant? So I would like to show you some interesting visualization. I very much recommend like Eyes on the Solar System. It's a simulation, web simulation from NASA, which lets you compare different celestial bodies, spacecrafts, distance between them, sizes. And here we have the largest moon in our solar system, Ganymede, compared with Mercury. Mercury is 7% smaller than Ganymede, which is interesting because like Mercury is considered a planet. The 3 I think rules that are to describe some celestial body as a planet is that it has to orbit the sun. So moons already failed it. Because they're orbiting other planets or dwarf planets. They have to clear their atmosphere from the natural rock debris, and they have to have enough gravitational field to have a spherical structure. Also, NASA has confirmed that as of state, I think March of 2025, we have around almost 900 moons in our solar system, 891, I think, and more than half of them are from dwarf planets, because we have more dwarf planets than just Pluto. We have Sedna, Eris, Oumuamua, Makemake. So now I would like to also show you these figures with 3 interesting celestial bodies to compare to Earth's moon, which is the moon that I think most of us know the most about, Pluto, so the dwarf planet, and Mercury, the smallest planet in our solar system. You can see that both Titan and Ganymede, two largest moons in our solar system, are larger than Mercury, also than Pluto, but significantly more than Pluto. Now I would like to move to discussing those moons one by one, starting with Titan. I won't be giving you, I think, very much information. I would more like to describe interesting facts about them, what's different them from the others. So first is Titan. Titan is the second largest moon in our solar system. It's like 2% smaller than the Ganymede. Its sole celestial body or place in our solar system that we know of that has like Earth-like fluid cycles because of its dense atmosphere that is made mainly from nitrogen and methane. There are fluid cycles like it's raining, there are flow of rivers, lakes, oceans. However, most of those fluids are methane. However, we are believing that under the surface of the Titan, there is ocean of water. Also, Titan is the only moon in our solar system that has a very dense atmosphere. Next, I would like to move to Enceladus. It's the smallest of the moons that we are discussing. However, we know that it has some water reservoir because in 2015, Cassini probe flew through the plume, so the geyser of the water that was ejected onto the surface and atmosphere with high velocity. And Cassini was able to go through this plume and collect data. It discovered that mainly this plume was made from hydrogen, so one of three necessities of life. The other is oxygen, third carbon. Okay, so next moon is Triton. It's only large moon of Neptune. There's interesting thing happening on the Triton because it has active geysers. However, they are not caused by the ocean. I think we think that they are not caused by the ocean, but rather the solid state greenhouse effect, because the icy crust of Triton is made out of nitric ice, and solid state greenhouse effect is an event in which, like, if it's the subsurface is heated up from the sun rays, the liquid is melted and there's a buildup of this liquid, and it's because of the high pressures. There's a crack in the structure of the crust of the Triton, and the nitrogen is ejected onto the surface and atmosphere of the Triton. Next one, we have Ganymede. It's Callisto, sorry. It's Callisto. It's the most cratered moon in our solar system. It's also, I think, the least one that we suspect from having subsurface oceans of these 6 moons. However, in 1990s, Galileo probe revealed that there may be a salty ocean underneath. However, it would be much deeper into this subsurface of Callisto. So now we are moving to Ganymede, and it's a largest moon in our solar system. It's one of the 4 Galilean moons, and there was interesting event because in December of 2005, Cassini probe and Galileo probe were in, I would say, similar distance from each other, because Galileo probe was passing near the Ganymede, and Cassini was using Jupiter's gravitational assist. And with that, we were able to measure simultaneously at two distant points the magnetic fields. The Cassini was responsible for the magnetic field mainly from the Jupiter, and Galileo measured the magnetic field from Jupiter and Ganymede simultaneously. So it was measuring the net magnetic field. And what's interesting, there's not only induced magnetic field from the Ganymede, but also Ganymede has its own magnetic field from the molten core that is probably made of iron 2 sulfide, or nickel. And because of this molten core, the flow of this molten core, there's magnetohydrodynamic dynamo. It's an interesting thing. This is what's responsible for creating the magnetic fields. What's interesting that the Triton, Mars, and Mercury, which are similar size as the Ganymede is, they do not have their own magnetic field. Also, why Moon has a molten core? Isn't it too small to have it? So what's interesting that there's between the 4 Galilean moons, especially between Io, Europa, and Ganymede, there is interesting synchronization. Every time Ganymede orbits Jupiter once, Europa orbits around twice, and Io orbits 4 times. And I will be discussing it a little bit later, but the changes in gravity from Jupiter and those moons that are passing near each other is making their cores squish and extend, which is producing friction, which is producing heat. So that's why the core is molten. Yeah, I think what's also interesting that in April of 2023, European Space Agency sent JUICE, which is Jupiter Icy Moons Explorer, interesting name, which will be responsible for gathering data of the Galilean moons, and it will overlap with Europa Clipper mission, because Europa Clipper mission is on 2030, and JUICE is expected to arrive on Jupiter's orbit July 2031. So now I would like to move to Europa, the case study, and firstly I would like to discuss the general structure of Europa. So we believe that Europa has icy crust that's around 15 to 25 kilometers thick, and underneath there is a subsurface ocean, which is around 60 to 150 kilometers deep. You can see here on the picture from JPL Caltech that there are like reddish orange fringes. We believe that most of them are hydrated sulfates, hydrated salts. Usually, mainly we are considering magnesium sulfate, and also we are considering not an ice but sulfuric acid. So with combination of the ice, they are producing such colors. And those fringes, we believe that are also fractures in ice. So there may be the chemicals from the ocean underneath. Okay, so also why there's a liquid ocean on the Europa? Like the surface is frozen. Why it's Europa is too small to have its fusion reactions in the core. It doesn't have a molten core that's creating like magnetic field. However, the same as with the magnetic field of Ganymede, because of the tidal heating, so the like remote heating of the gravity of Jupiter and other moons, the core of Europa is squished and extended, and this heat, the friction produces heat, which is making the water liquid. We also believe that there's twice as much water in Europa than it is on Earth, which is interesting because Earth is like 4 times as large. Now, I would like to discuss solar wind, radiation, and the magnetic field. So, main dangers around the exosphere of Jupiter. The picture on the right is directly taken from the book. I have translated the descriptions, but I would like to focus on solar winds first. So the sun is ejecting ionized particles, mainly hydrogen ions, which then are redirected by the magnetic field of the Jupiter around its orbit, around its exosphere. You may know that the magnetic field and solar wind is responsible for auroras on the north and south pole of Earth. Jupiter also have those auroras, but the problem is that though the ionized particles are spread across the orbit of Io, Ganymede, and Europa, which are hitting the surface, which is quite dangerous. So the surface of those moons is not habitable. The only thing would be habitable is the oceans underneath. Also, there's radiation, which is very dangerous. However, it's the icy crusts protect the oceans from it. Next, I would like to move to gravitational well of, maybe move back, because I said that I will mention MASPEX. What's that's the instrument that was not the MASPEX. MASPEX, yeah, I think MASPEX, which was responsible for gathering data around the gases. Also, the thing that was responsible for it was PIMS. Yeah, PIMS, because it was electrical current produced by plasma measurements. So the plasma that is charged is moved around and spread around the Jupiter's exosphere because of the magnetic field, and ECM and PIMS will be measuring those values. So that's the direct instrument that's responsible for it. Yeah, that's the reason the PIMS exist. So next one is gravitational well of Jupiter and Europa. You can see it's also the graph taken directly from the book. You can see that Jupiter has an enormous gravitational field, which is influencing also the net gravitational field around the Europa. So when the Europa Clipper will be moving around the Europa, the gravitational field between of the side of the Europa that is facing the Jupiter will be differently shaped because of the gravity. So with those difference in gravity, we'll be able to measure the mass distribution on Europa. That's why we have GRS, gravity and radio science. So it was about the radio waves that are sent between Earth and Europa Clipper. And those radio waves will measure Doppler shifts. So if the mass will be pulling a Clipper faster, so it will be accelerating the Clipper or decelerating, we'll be able to measure it with GRS, and with the differences of the position and expected position of the Europa Clipper, we'll be able to measure the gravitational field on parts of Europa. Okay, and next one, I would like to mention one researcher. It's Vasily Ivanovich Moroz. I think there's different spellings of his name. However, I have stumbled the most often on this one. And in 1966, in journal named Soviet Astronomy, I think exactly on volume 9, page starting 999, he made an article looking at the Galilean moons and the albedo, also their spectra. And I think he's the first person and his team that was investigating those moons more closely. You know, the Galilean moons are named after the Galileo who discovered them. However, I think that Moroz is also a very important person here because he contributed a lot towards what we already know about those moons. I would like to, from this article, I have taken 4 figures. Those are the spectra of the Io, Ganymede, Europa, and Callisto. I would like to focus on the bottom left spectrum. Its range is between 0.7 and 2.5 microns. And you can see that on 1.4 and I think around 1.8, there are significant decreases. And those decreases show us the fact that there's subsurface ocean underneath the Europa. However, interestingly, Moroz suggested otherwise. He firstly assumed that it's because of the atmospheres of Ganymede and Europa. We know that Europa has atmosphere which is very thin, and he calculated that because of the ice that is on surface of Europa, which is approximately 1 gram per centimeters cubed with density, at the temperature of 125 Kelvin, so quite low, the ice would melt in approximately 10 to the 7 years, so 10,000 years for this ice to melt, which seems a lot. However, those moons have billions of years, so none of them should have those ice crusts. So he said that's probably because of the significant atmospheres. We now know that also those discrepancies are because of the subsurface oceans. Now I would like to focus on the structure. So you can see here on the left, also from Jet Propulsion Laboratory, that there is part of the cross section of Europa. We have at the center its core, probably made of iron to sulfide or nickel. This core has almost 600, approximately 600 kilometers in radius. Next we have mantle, the brown area. It's around 800 kilometers in radius, starting from the surface of the core, and then we have 75 to 175 kilometers of water, both liquid and ice. And you can see here also the comparison between Earth and Europa. I said before that the diameter of Earth is 4 times more than of Europa. However, Europa has twice as much water, salt water, than Earth. What's also interesting, average ocean depth for Earth is 4 kilometers, but from Europa is 25 times more. As I said before, it's between 60 and 150 deep, the saltwater ocean. Now I would like to more deeply discuss interesting thing that's connected with measurements on Europa. We will go a little bit in depth about moment of inertia of Europa. Some of you may know that moment of inertia in spheres is like the analogy equivalent of mass in a linear motion. We have rotational motion, and we have moment of inertia, we have linear motion, and we have mass. And here I have shown two values for the solid sphere with evenly distributed mass. Its moment of inertia is 2/5 or 0.4. The m is the total mass, and r is the total radius of the structure. For the thin spherical shell, so when the mass is mainly distributed on the outer layers of the structure, the moment of inertia is 2/3 mr squared. So from this, we can conclude that the more the mass is distributed on the outer layers, the greater is the moment of inertia. And it makes sense because it's like harder to stop this body. We can interpret it as the moment of inertia is how hard it is to stop the specific structure from rotating. You can also deduce from this that from most of the celestial bodies, I think all of them, we expect moment of inertia to be smaller than for the solid sphere even, because the mass is not distributed on the outer layers, but on the core, because cores are way denser than the outer layers. So the more mass is concentrated inside. And I would like to also mention that here m and r are the same. So it's like the total mass and total radius are the same. The only thing that we are interested about here are the coefficients, so how it is distributed. And you can see here the title for the article that I have taken this graph from. And the researchers made a model, tried to make a model of layers of Europa. They have shown that the two-layer model, so the just core and mantle, cannot be, because the distribution, the mantle and core have too much density, so they would it will be too evenly distributed. The mass will be too evenly distributed, so the values of moment of inertia would be very similar to 0.4. However, from the, I think, Galileo measurements and DSN, so Deep Space Network, we have gathered that the empirical values for moment of inertia for Europe is 0.346. So it's smaller than the solid sphere, and this is what we expected because the mass is more dense inside. And here is a very interesting graph. We have like three dimensions: rock density, ratio rock radius, Europa radius, core radius, Europa radius, and we have ice density. Ice is here considered both as water and ice, the liquid and ice, because they have a similar density, around 1.0. Ice is a little smaller, I think 8% smaller. However, along these three dimensions, we also have colors, which suggest the thickness of the ice layer. So we have the fourth dimension, and if we are very eager, we can consider these two graphs as another binary dimension. So it's here we have iron to sulfide core, or just iron core, and we'll have a very pretty 5-dimensional graph. And you can see that if we would increase the rock density, so the density of the mantle, would increase the core radius to Europa radius, because core radius we expect it to be around the almost half of the radius of Europa, total Europa radius. And if we increase ice density, we see that those models show that the thickness of the ice layer also have to increase to compensate for the density of the rocks of the core. This is because if we increase the rock density and core radius, we'll see that the mass will be more evenly distributed. However, to compensate for this, because we want smaller values for moment of inertia, we'll have to increase our expected thickness of the ice. So you can see that for very large values, the thickness of the ice is 200 kilometers. We are expecting something in that range from like 60 to 175. And from these graphs, we can see what are the possible values of this measurements. And having 3 or 4 values, we can suspect what will be the fourth or fifth one. Okay, so now we'll be slowly closing in. I would like to discuss the potential view from Europa. It's like the artistic rendition. We know that it's simple that the view from Europa will be dominated by Jupiter, which will be 24 times larger than the sun that we see from Earth, because the sun and moon, they are similar angular size. We're measuring here the angular size, and moon from Earth has around half a degree of angular size. Jupiter from Europa has 12 degrees, so 24 times larger. If we could see magnetic field of Jupiter, it would not only dominate Europa's view, but also view from the Earth. That's how large the magnetic field is. Also, we'll be able to, from Europa, we'll able to notice moons depending on their time of their orbits. Callisto will be, for example, half as large as the moon that we see from the Earth. Both Io and Ganymede on their closest to Europa, so the higher angular size that we could measure from Europa would be around 50% larger than Moon. So the view would be pretty beautiful with like the gigantic Jupiter and 3 big moons, and also other small moons that are orbiting Jupiter together. Okay, and now I would also like to discuss, because I kind of skipped this, what's the reason for sending the Europa Clipper? Because yeah, we're not expecting to find it under subsurface oceans, I don't know, like squids, octopi or something. More likely we are expecting that the subsurface ocean will be like analogy to primordial soup on the Earth. So it will be like environment that could spring life in some future. If we would be very lucky, we could see maybe like single cell organisms or like structures that could resemble them. Also, I think what's important, we also we want to measure how habitable Europa is. So, for example, you would like to colonize it in the future, what we would have to prepare for. So I would like to now compare it with the Earth's timeline. You can see that I would like to more focus on this gray part. Earth, similarly as Galilean moons, have around 4.5 billion of years. They they formed around 4.5 billions of years ago. Here on this graph, we can see 2,500 millions of years ago, thousands of millions of billions, and the first life on Earth is from more than 2.5 billion years ago. It's a cyanobacteria that's, I think, on stromatolites, and it was the first photosynthesizing organism. So we can see that if we exclude the Hadean period, because Hadean is mostly the surface of the Earth was molten and it was just getting there was a lot of heat on the surface, so there was no really chances for the organisms to spring to life. So we are mostly interested in Archean, and we can see that at most 1,500,000,000 years after Hadean period, we could see the first organisms. So it's compared in the whole age of the Earth is quite quick. So knowing that there are oceans, subsurface oceans on the moons that are also have similar age. And for example, in case of Europa, the ocean is twice as large as it is on Earth. We could suspect that maybe there are some at least singular cell organisms. However, we are more expecting like this, as I said before, measuring the habitability and the maybe the primordial soup-like compounds. Okay, so I think that's it. Now, references and recommendations. If somebody is interested in more like in-depth technical stuff, I would very much recommend Space Science Reviews. That's the journal that it's open access, if I'm correct, and it has a lot of great articles. There's, I think, connected with Europa Clipper around 18 articles, and for example, here is the mice instrument deep analysis. I think it's around 40 to 60 pages long. So if someone is more interested in this in-depth analysis, I recommend it. Also, Eyes on the Solar System was the web simulation that we are comparing Ganymede and Mercury. It's great for those kind of things. You can just open it on a browser. Also, ESA.int is the European Space Agency website, which also has great articles, especially if you are interested in JUICE mission, so Jupiter Icy Moon Explorer. It's under this site.esa.int web JUICE. Also, the book Alien Oceans by Kevin Peterhand is, I think I have them here somewhere. Which I something to choose. Tony. I think I have forgot about it. So it's Alien Oceans, a search of life in depths of cosmos. And yeah, if somebody has any questions, I would like to answer them if I will be able to, and if not, I will at least hope I will be able to redirect you to relevant resource. So for the books similar to Alien Oceans, so I think I'm prepared. That's a good question because I'm prepared for it. More general, I have recently started reading is Cosmos by Carl Sagan. I think there's also Błękitna Kropka Blue Dot. I think it will be something like that, Blue Dot by Carl Sagan. They are more about the general our solar system and space itself. The Alien Oceans is more about the 6 moons I have mentioned. There's also National Geographic books. I think there I have 2 around me. One is Atlas Kosmosu, Wszechświat w niskiej częstotliwości, so universe in low frequency, and the second one is like the opposite, universe of high energies, so high frequencies. Also, I have some of the information that I was inspired to make this webinar was with Lucy and Stephen Hawking book. I have the German version, Der geheime Schlüssel zum Universum, and also from the German source about like the general popular science. I have Der Ursprung des Universums, and I think that if you are more interested in like popular science, I would very much recommend Carl Sagan. He was like my first experience with the popular science books connected with astronomy.